Push the button. All right, let's head on up. What's that? Bathroom scale in an elevator. That's weird. Oh, I get it. Like I'll be heavier when I'm going up in the elevator. Okay, cool. Let's give it a try. All right. Not quite 150, looks like. We'll push the button. Yep, I knew it. Heavier on the way up. That's not heavier anymore. Whoa, went lighter for a minute there. Well, that's weird. Let's see, is anybody around here? Nope. Now let's go back down. It's going down on an elevator, so I should be lighter on the way down then. Let's give it a shot. Yep, lighter. Not lighter anymore. Weird. Heavier for a minute there. What is going on? Riding a bathroom scale on an elevator may not seem like a real common event, but I can assure you in the physics community, everybody knows about this situation. This is just part of physics culture, is this idea of riding on a bathroom scale in an elevator. I think every physics class I've taken where we've discussed Newton's laws, we've worked this problem at least once. It shows up on the AP test all the time, and when I was at Iowa State, we actually had a permanently displayed or permanently fixed bathroom scale in the elevator in Physics Hall. So this is something that I would be remiss if I didn't share with you. The idea here is that by our intuition, we might expect that as we're riding upward in an elevator, we are going to feel heavier, and then the scale then, as a result, is going to show a larger number. And conversely, if we're riding down in an elevator, then we're going to feel lighter, and the scale is going to read a smaller number. But as we've seen, it's a more complex relationship than that. Our intuition here does not do a good job of predicting what we're going to get for our changes in forces. So let's look at why that is. Now, first off, we need to dispel this misconception that we have that when we step on a scale, it's measuring our weight. In fact, it doesn't measure our weight. It has no ability to measure anything other than this motion within the scale itself. The scale, a basic version of the scale, bathroom scale, is that we have this plate here that can shift up or down, and it's resting on a spring. And there's some other mechanisms that help to convert motion like this into motion on the dial. But in short, when we step on the scale, we're just compressing a spring, and then there's a conversion that takes place in the mechanism of this device to tell, if we compress this spring by a certain amount, then what force are we exerting on that spring? And it turns out that springs will compress at a predictable rate when we apply a certain force to them. So if we apply a force downward to a spring, it compresses a little. If we apply double that force, it'll compress twice as much. That gets into a relationship called Hooke's law that we'll do more with later on. For now, though, we just need to understand that what's really being measured here is a distance that this plate moves downward, and that distance corresponds to the force that's being applied to this spring. And since Newton's third law says that when two objects act on each other, they each experience a force that's equal in size and opposite in direction, this spring is being pushed downward by our feet, presumably, which means it's also pushing upward on our feet. Now, that upward force is what, when we're standing on the spring, is what keeps us from falling through the spring. And in some cases, that upward force would have to be equal to a downward force from gravity on us, but not in all cases. So let's look at those cases where that wouldn't be true. When we stand on a scale, which remember is just a spring with a platform on top of it, we experience two forces. We get pulled downward by a force of gravity, and we get pushed upward by the spring. Now, you might be tempted to then think if we're moving upward, then we must have a bigger upward force than downward force. But that's not what Newton's laws would say at all. Newton's laws don't say that the velocity is in the direction of the net force. They instead say that the acceleration is in the direction of the net force. Acceleration equals net force divided by mass. If we have zero acceleration, we must also have then a zero net force. Zero net force here would mean that the upward force and the downward force were the same size. So in this example, that F spring will be equal to F gravity if acceleration is zero. Now remember, that can happen in a couple of different ways. We could have our object at rest, our person is at rest, but they don't have to be. As long as they have constant velocity, whether the velocity is zero or some other value, as long as it's constant, we have acceleration as zero, and those two forces are going to be equal in size. We could also have the spring force become larger than that gravitational force. And that would happen if we have an acceleration that is upward. So if we're riding in the elevator and it starts to accelerate upward, so we're at the bottom floor and we're starting to move upward, we'll have the spring force be larger than the gravitational force for a little while, which means the scale is going to show a larger value than your actual weight. And then we could have the opposite here as well. If the spring force can be less than the force of gravity. Gravity stays constant, but that spring force changes as the amount of compression changes. And that's going to happen if the acceleration is downward. So if we're starting up at the top and beginning to move downward, acceleration is down, that spring force is less than the force of gravity. Now it can also happen while we're slowing. So I've just talked about it speeding up, but that spring force would be greater than the force of gravity whenever we're accelerating upward. That could mean that we're moving upward and getting faster, or moving downward and getting slower. So on the way down, at the end of our trip, when we're slowing to a stop, we're going to find that spring force is larger than the gravity force again. So the reading on the scale goes up. For the spring force being less than the force of gravity, that happens when acceleration is down. That could be when we're getting faster while moving downward, or it could be while we're getting slower and moving upward. So as we're approaching our floor on the upward trip and we start to slow down to a stop, we have downward acceleration. That would mean the spring force being less than the force of gravity, and so our number on the scale is going to get smaller. Now let's put these ideas into a calculation type problem. So we have a person who's riding on an elevator, and we see the measurement on the scale in the elevator, and from that information, we're going to try and determine the acceleration of the elevator. First step in these problems is to identify forces that are acting on our object. So we've got our person, and just to keep the drawing simple and be consistent with what the AP test will have us do for free body diagrams, instead of a person, I'm just going to draw a dot. That's our object. This dot, this person, has a downward force acting on them, and that's Fg, the force of gravity. And they have an upward force acting on them, and that is Fs, the force from the spring. Now, here we are told that the scale shows a measurement of 600 newtons. That is going to be the force that's acting on the spring, or the force that the spring is providing to the person. Same size force, that's a Newton's third law idea. The force of gravity acting on this person isn't given to us, but we can calculate force of gravity by multiplying the mass of the person times the acceleration due to gravity. So then force of gravity is equal to 60 kilograms times 9.8 meters per second squared, and we get a gravitational force of 588 newtons. Now the question asks, what's the elevator's acceleration? We don't really have any information about the elevator, but presumably the guy who's standing in the elevator is going to be accelerating the same way that the elevator is. Otherwise, he's got problems. So we're actually going to solve for the person's acceleration rather than the elevator's acceleration. And we know the mass of the person, and we know all the forces on the person, so this now is a Newton's second law problem. So Newton's second law says the acceleration is equal to the net force divided by the mass. And acceleration is our unknown, so we'll leave that as A. Our net force, we're going to have a positive 600 newtons and a negative 588 newtons for that gravitational force. And then we're dividing by the mass of this man, which is 60 kilograms. Up on top, that positive 600 and negative 588 gives us a positive 12 newtons for our overall force. And down here we've got 60 kilograms, which leads us to an acceleration of 0.2 meters per second squared, and that is in the positive direction. Well, anyway, we've got a lot of problems that resembled this one that we might draw from. All sorts of variations. Maybe instead of a person on a scale, it's an object hanging from a string, and we're looking at tensions in the strings. But regardless, the idea is that we're taking a situation like riding in an elevator, which brings up some intuition that may be wrong, and we're trying to challenge it. I think these problems are so difficult because we're not used to standing in a frame of reference that's accelerating. So if I'm standing on the floor, not in an elevator, just on the ground, and suddenly I feel extra force in my feet, that probably only happens to me if, say, somebody comes up behind me and starts pushing down on my shoulders. So I would expect then that means I have some extra downward force on me. And I know that the downward force on me usually is gravity, so I might lean toward, gravity has become a bigger force here. So really, these questions from a Newton's second law standpoint aren't typically all that tough, but they do bring out some misconceptions that we might have about what causes these forces to change and what doesn't cause forces to change. What force we are actually measuring here, the spring force instead of the gravitational force. And also when we expect to have an unbalanced force. Is it when we have motion? Well, no. Motion by itself doesn't tell us we're going to have unbalanced force. It has to be accelerated motion for us to know that there's an unbalanced force. So really a lot of conceptual understanding required to answer questions like these. And then once you get there, the math we see is not overly difficult, so we don't have to stress out too much on that part of the problem. Thanks very much for watching, folks. If you found this useful, please like and share so other people can find it. And if you think you might find future videos useful, go ahead and subscribe. Take care.